Welcome to the third video where we are looking at Bernoulli Euler problem. Basically, it's a problem which is commonly known as the problem of misaddressed letters. That is, letters ending up in the wrong address or the wrong recipient. It's a very interesting case, and we'll be looking at what it basically deals with, and also going forward looking at we'll look at how to derive a general formula. Now for letters, let's look at letters L1, L2, L3 all the way up to Ln, and naturally the envelopes for them, that is envelope 1, envelope 2 all the way up to envelope n, having their respective addresses. That is the address 1 basically deals with the envelope in which the first letter should be kept. Likewise, address n means the correct address for the nth letter. Naturally, these letters should be in their respectively addressed envelopes. Now, what if that's not happening? What if all the letters are ending up in the wrong envelope? That is, the address obviously is wrong, which means that none of the letters would be reaching the right recipient, or all the letters would be going to the wrong addresses. This is what is basically meant by the Bernoulli Euler problem, and we'll be looking at this interesting case in Permutations and Combinations. So it's a case where the addresses are wrong, which means that the letters are kept in the wrongly addressed envelope, and not the point that this mathematical concept, it's called derangement, and derangement happens when all the values are not in their intended positions, which means that in this particular case we are dealing with all the letters are not in the correct envelope, which means that none of the letters would reach the correct destination. So in derangement, we'll be looking at how many ways this misplacement can happen. What are the ways in which the letters can be kept in the wrongly addressed envelopes? That's what is we are dealing in derangements. And so before going into the details of derangement, we'd also look at what exactly we are dealing with. So in this video, we'll be looking at generating a theory for derangement, and also going for what is the equation of derangement if we are dealing with n objects. So objects basically the natural numbers, that's 1, 2, 3 all the way up to n. Now the key point here is that we never write something like 1, 2, 3, 6, 4, 9. Why? Basically because each integer has a particular position. There's a placement value. There's a position value for each integer. That's each place, each position has a definite value or as a intended value. That's the meaning of it. So it also means that the second position is something like comes between the first and third. Fourth one should be coming between the third and fifth, and going on to the nth position. This also means that each position would be denoting a placement, or something like a box or a compartment, or in the particular case we are dealing with something like the first letter should be in the first envelope, something like that, which obviously means that the nth letter should be placed in the nth envelope, which is the envelope meant to be basically dealing with the nth letter. So the nth means the nth box, or the nth letter, or the nth placement, something like the nth compartment. And so derangement basically means when the placements are totally not rightly done. Now, what's a true derangement? Or derangement occurs when none of the placements are right. For example, in this case, 1, 2, 3, all the way up to n, if none of the placements are right, for example, we can see that the first letter or the placement is in the, I mean, it's going to the third position, something like so. None of the values are in the intended position. So that is true derangement, or simply that's derangement dealing with. That is, none of the values are in the intended position. So in the case we are discussing, something like none of the letters are in the envelopes in which they ought to be. Only in such a case we can call it a derangement. Now let's look at how we can derive a general equation for derangement using a simple process, a simple mathematical thought process. And here we'll be using, of course, the case of letters. And later on, further, we'll be looking at what's the general formula for derangement dealing with n objects. So, using letters, we can do it in a simple, a clearly understandable manner. So let's look at the case of 4 letters, a simple case of 4 letters. And let's begin with the first letter. So understand that first letter means that there will also be a single envelope, that's an envelope for that letter, which means that for a particular letter, one letter, there will be one envelope, which means that this is a case in which derangement is not possible. Why? Because there's an envelope for that particular letter, or the placement is, there cannot be any misplacement. There cannot be a case of putting letter in an envelope which is not intended for the letter, which basically means that for one letter, that is for one object, derangement is 0. And derangement is generally denoted by capital D, which means that for one, D1 is equal to 0. So for one object, there's simply no derangement. What about 2 letters? That's letter 1, letter 2, and we have the related envelopes. And we can easily see that the second letter can be placed in the first envelope, and the other way around. I mean, the first letter can be placed in the second envelope. So there's one way of doing it. So totally for the objects, there's a single way of doing a derangement. That is, for the first letter, only one way of getting it deranged. Second letter, again, only one way of getting it deranged. So it basically means that when we are dealing with 2 objects, D2 is equal to 1. Now, what about 3 letters or 3 objects? So now for 3 objects, let's look at how the derangement works. So we have the letters L1, L2, L3. We have the 3 envelopes, and let's look at the combinations in which the derangement can be done. So what I am going to write here, that combinations would be looking at the placements into which letters are kept. So we are looking at all the possible combinations. So beginning with 1, 2, 3, and 1, 2, 3 is the case in which naturally there's no derangement, because it means that the first letter is going into the first envelope like that. Second to second element, third to the third envelope. Now, so we can see that there are 6 cases of the way in which the letters can be kept in the respective in the envelopes, and it can be easily seen that in all these 6 cases, only in 2 cases there is true derangement. True derangement in the sense that all the letters ending up in the wrong envelope. For example, if you are taking 2 and 3, it's not a case of derangement because the third letter is going to the third envelope. But in cases of 2, 3, 1 and 3, 1, 2, we can easily see that none of the letters, in such a placement, none of the letters would be ending up in the correct envelope. So only in 2 cases we have derangement. Naturally, D3 is equal to 2. Now, we are going to the case which we intend to do that. So what is the case of 4 letters? And so let's do it. Let's get the thing in a, let's do the calculation in a step-by-step manner. So for x1, basically it represents the first letter in the first envelope or the first value in the intended position. And as we are dealing with 4 letters and the other 3, there will be 3 factorial possibilities, which basically mean that there are 6 possibilities for the other 3 letters. So what does this deal with? This is the same case if we are dealing with x2, x3 or x4. In all those cases, each of one of them has one case where the value would be in their intended position, and 3 other possibilities would be, 3 factorial other possibilities would be coming up. So in all cases, one letter ends up in the right envelope. And of course, for the other 3 letters, there are 3 factorial combinations. So so the right positions, one each for x1, x2, x3, and x4. What does that mean? It means that for for all the 4 letters, we have something like, there are 4 times 3 factorial ways for a particular value, in this case a letter, to occur in its natural position, which basically means that its intended position, or in this particular example, the envelope in which it should be there. Now, going on, we are looking at the case of, what about x1 intersection x2? Of course, once again, as we have already discussed just now, for these 2 cases, there's one letter and the second letter. One way to place 1 and 2 values, that is 1 and 2 letters in their corresponding positions, and for the other 2, naturally there will be 2 factorial combinations which are possible. So one way to place 1 and 2 letters in their natural position, and then 2 factorial ways to place the remaining values. And not the remaining values, we are looking at the envelopes. And to put it in a diagrammatic manner, letters L1, L2, L3, L4, and envelopes E1, E2, E3, E4. So what we just discussed is L1 ending up in E1, which is its intended placement, L2 ending up in E2, which of course is the intended place for L2, that is the natural, those L1 and L2 cases are the natural positions, and the other 2 having a combination, 2 ways to do it, 2 factorial, that is 2 ways to do it. Now, so what does it mean? In other means, or in other words, for 3 letters, the total pairs would be 4C2, that is 3 factorial, which is 6. So there will be 6 pairs, which implies that there are 4C2 times 2 factorial ways for 2 values to simultaneously occur in their natural positions, or to put it in the way in which we are doing the problem now, that much ways to place the letters in their intended envelopes. Going on further, likewise for x1 intersection x2 intersection x3, what is the case in this particular situation? Of course, once again, it can be easily seen that one way to place the letters or the values 1, 2, 3, their corresponding natural positions or the natural orders, here referring to the letters, and remaining for the 4th letter. Of course, there's only one factorial or one way to keep it. Naturally, that 4th letter, it basically means no derangement is possible for the 4th letter. So, expressing it by means of combination, that is 4C3 times 1 factorial, that is 4 ways for 3 values to simultaneously occur in their natural positions, or 4 ways for the 3 letters to simultaneously occur in their respective intended envelopes. Now, we have discussed till 3 letters. What about the 4 letters? That's a case which we have taken. What about 4 letters? As we are looking at x1 intersection x2 intersection x3 intersection x4. Interestingly, it's easily seen that for this case, there's only one way. Only one way all of them can be kept simultaneously kept in their natural positions. So only one way to place all the 4 values here, the letters in their natural positions, that is the respective envelopes. Envelopes means the corresponding right placements. That is for letters L1, L2, L3, L4, and the corresponding envelopes E1, E2, E3, E4. We can easily see that there's only one way it can be rightly placed. So to sum up, the total the calculation is 4 factorial minus 4 times 3 factorial plus 6 times 2 factorial minus 4 times 1 factorial plus 1. So we'll be getting 9. So here we have used the inclusion-exclusion principle. And by using that principle, we can easily see that derangement for object number 4 is 9. That is D4 is 9. And we have used the inclusion-exclusion principle for that. Now from here, we can derive a general formula for this four letters or 4 objects. What about n objects? That's what we are going to calculate now. So what exactly have we done here? What is the procedure we have we did here? So here first we calculated the number of permutations of the intended values. So naturally we chose 4 letters. That's so the objects were 4. That's 4 factorial. Then we subtracted from that the number of ways to keep at least one element in the natural position. That is one letter in its intended envelope. Then went on to add the number of ways to keep at least 2 elements in their natural position. So number of ways to keep at least 2 values in their natural position, and then from that subtracted number of ways to keep 3 objects in their natural position, and finally added the number of ways to keep four objects or four values in their natural position. So you can see that it's a alternative subtraction addition based on the inclusion exclusion principle. So it's totally it's 4 factorial minus 4 times 3 factorial plus 6 times 2 factorial minus 4 times 1 factorial plus 1, that's 9. So for D, for 4 letters, that is when n is 4, the answer is 9. The derangement value is 9. We can rewrite this as 4c0 times 4 factorial minus 4c1 times 3 factorial plus 4c2 times 2 factorial minus 4c3 times 1 factorial plus 4c4 times 0 factorial, which can be rewritten as 4 factorial by 4 factorial times 1 factorial the whole times 4 factorial minus 4 factorial by 3 factorial times 1 factorial the whole times 3 factorial plus 4 factorial times 2 factorial times 2 factorial the whole times 2 factorial minus 4 factorial by 1 factorial times 3 factorial the whole times 1 factorial, and lastly times 1 plus 4 factorial by 0 factorial times 4 factorial the whole times 0 factorial, and cancelling off the common factorial. So we can easily see that there's an interesting pattern coming up, that is 4 factorial by 1 factorial minus 4 factorial by 1 factorial plus 4 factorial by 2 factorial minus 4 factorial by 3 factorial plus 4 factorial by 4 factorial. So it's a very interesting pattern which is emerging, and as 1 factorial is 1 and also 0 factorial is 1, we can write the first division, the division as 4 factorial by 0 factorial minus 4 factorial by 1 factorial plus 4 factorial by 2 factorial minus 4 factorial by 3 factorial plus 4 factorial by 4 factorial. We can easily see that the denominator values is increasing as we go forward. I mean, as based on the n, that is 0 to 4, where in this case we choose n as 4, which means taking out the common 4 factorial, it's 4 factorial times the whole of 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. So that's for n is equal to 4. What about n objects? So we are looking at deriving the general formula for, so dn is equal to n factorial times the whole of 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial going all the way up to plus minus 1 raised to n factorial times 1 by n factorial. So that's the general equation for derangement of n objects. Let's get the result through an interesting recursive determination process. So what's this process? Let's take a particular case where we have the values and 1, 2, 3, k minus 1, k plus 1 going up to n, and we have derangements, so k, where we have derangements where only two particular values are known. I mean, one has gone to k and k has gone to 1. So which means that k and 1 has traded position. So 2 integers are deranged. All other integers we don't know the derangement, which means that further derangements, 2 minus 2 integers are left to be further deranged, or those derangements there's no information about. So those derangements can be of course done in n minus 2 ways. Now what if we only know about a single derangement, that is one which has ended up in the k placement, and all of the derangement values it's not known. So one has ended up in the k position, that is the only thing we know, which means that n minus 1 derangements are left, which means of course dn minus 1 derangements are to be done. So case 1 dn minus 2, case 2 dn minus 1. So case 1 plus case 2 of course will be dn minus 1 plus dn minus 2. Now there's an interesting fact we should look at, that is how many integers can be put in the position I mean in the first position to carry out this, obviously that is only n minus 1 integers. So obviously all integers except 1, which means n minus 1 integers. So dn would be n minus 1 times the whole of dn minus 1 plus dn minus 2. So, and what is the interesting about this? What is important about this? So the key point here is that if we already know the derangement of the earlier values or the beginning values or the first values, we can subsequently calculate the values for the higher derangements. So the key point is that knowing the lower values can be used for finding further higher derangements. Now, finally, let's look at another interesting way to look at explain derangement by fixed point permutation. Let x is equal to, x is a set of 1, 2 all the way up to n, and k be a bijective mapping between x and x. Then k is called a permutation on x, and this can be of course written as 1, 2, 3 all the way up to n, and for k1, k2, k3 all the way up to kn, which means that for I, which is an element of x, if ki is equal to I, then I is called a fixed point permutation, or fixed point of the permutation k on x. That is, the number of permutations with no fixed point would be actually the derangement of n objects. So that's very interesting. So the number of permutations with no fixed point actually would be looking at the total, the derangement value. So the corollary, we can consider derangement as a bijective mapping, say between x and x without a fixed point in the number of permutations on x. Thanks for watching this video. Thank you.